Somewhere in deep space, there are things that shouldn't exist according to the laws of nature we know. Stars that blink in strange ways, impossible light patterns, structures so large they make planets look like grains of sand. For decades, astronomers have detected mysterious signals coming from space. Lights that dim and brighten without explanation. Objects that move in ways that defy everything we know. Tabby's star was just the beginning. It lost almost half its light in ways no planet or asteroid could cause. Now imagine this. What if ancient civilizations, billions of years older than ours, built things so massive around their stars that we can see them from Earth? What if these giant structures, spheres collecting solar energy, enormous rings around entire suns, aren't just theory but reality waiting to be discovered? Prepare yourself for 2 hours exploring the most convincing evidence that we're not alone, and that out there exist engineering works so vast our minds can barely comprehend them. Subscribe to the channel, leave your like and comment from what part of the world you're watching. Get comfortable and relax. Let's begin. Have you ever wondered if, right now, there's something out there orbiting a distant star, changing its light in a way that only a super-advanced alien civilization could pull off? This is not just a question for science fiction movies. Since the middle of the 20th century, scientists have been straining their eyes and telescopes looking for signs that intelligent life has built massive projects in space, alien megastructures on a scale we can barely imagine. It's a big idea that started as a scientific hunch and grew into one of astronomy's most fascinating searches. The story really kicks off in the 1950s and early 1960s, a period when space exploration was beginning to shift from fantasy to real science, with the launch of early satellites and the first robotic missions beyond Earth. Back then, researchers started noticing strange irregularities in light coming from distant stars. These variations didn't always match up with expected behaviors like eclipsing binary stars, asteroid belts, or regular planetary transits. That was when the speculation began. Could these unfamiliar patterns be signals of something artificial, something constructed with a plan and purpose? It didn't take long for creative minds to connect these cosmic oddities with the idea of extraterrestrial life. In 1960, the physicist Freeman Dyson published a paper that fundamentally altered the conversation. He wondered, if an alien civilization kept getting more advanced, wouldn't it eventually need way more energy than a single planet could provide? What's the logical next step? Dyson imagined that such a civilization might assemble a huge shell or cloud of objects all around their star to capture as much of its power as possible. This theoretical creation soon became known as a Dyson sphere. Dyson's thoughts weren't just playful brainstorming, they were rooted in the mathematics of energy use and the physical possibilities of engineering on a vast scale. He reasoned that any civilization growing for hundreds or even thousands of years would need exponentially more power, and their home planet would only supply so much. So harvesting a star's entire energy output with giant structures seemed like a logical leap. If we, as humans, ever reached that level of technology, we'd probably try something similar. More importantly, Dyson left a trail of clues. If such structures are out there, they might give themselves away by blocking, filtering, or even re-emitting their star's light in distinctive patterns. That was the spark that set the search alight. Not all astronomers were quick to jump on board with the alien megastructure hypothesis, but the idea caught enough attention to inspire real observations. People started combing through data from the rapidly improving generation of telescopes coming online in the late 20th century, both ground-based and orbiting ones. They looked for stars that dimmed unpredictably, or flashed in ways not explained by known cosmic objects. Any signature that might have a non-natural cause suddenly became worth a second glance. And with every passing decade, as telescope sensitivity improved and computer software got better at chewing through huge datasets, the search for megastructures grew more systematic and ambitious. Along the way, scientists realized they had to know what they were looking for. After all, the universe is full of mysterious noise, cosmic dust, interstellar clouds, unforeseen types of variable stars, and complex gravitational dances between planets and their suns. Sorting out what's natural and what might just be unnatural became its own challenge. Researchers drew up lists of what a Dyson sphere might do to starlight. Perhaps it would cause a star's brightness to drop sharply, or to flicker in an irregular pattern. Maybe it would lead to a steady drop in visible light, balanced by a rise in infrared radiation as the structure absorbed energy and re-emitted it as heat. It wasn't long before other scientists kidded out even wilder possibilities. As telescopes reached deeper into the galaxy and technology improved, astronomers started to realize that megastructures might not always look like perfect, complete shells. Maybe the energy-collecting structures would be swarms, like dense clouds of orbiting solar panels constantly shifting and reconfiguring. Others suggested megascale rings, disks, or even entire nets of machinery laced around stars. Artistic as these ideas might sound, they provided practical criteria for what to look for: odd dips, strange periodicities in starlight, unexpected colors in a star's spectrum, or even clusters of stars producing too much heat to be natural. Meanwhile, the conceptual backbone for all this searching got stronger. As we moved into the 1970s and 1980s, more researchers formulated theoretical frameworks for what alien megastructures would imply. They realized that to even attempt such a feat, a civilization would need an incredible mastery of materials, energy, and long-term planning. The sheer logistics would be mind-boggling: mining asteroids, assembling machines in orbit, maintaining or repairing thousands or millions of gadgets floating in space almost indefinitely. But the flip side of such massive endeavors is that they would stand out, producing effects far more dramatic and unusual than almost any known natural event. All this fueled a new era in astronomy, one where the attitude was, keep an open mind and let the data guide you. While some researchers remained skeptics, a growing community worked up systematic ways to look for megastructures, studying not just stars, but sometimes entire galaxies for signs of energy usage or construction. The launch of powerful space telescopes like the Hubble in the 1990s and, later, missions specifically designed for planet hunting like Kepler in the 2000s added layers of sophistication. The Kepler Space Telescope in particular began generating detailed light curves for hundreds of thousands of stars, producing the kind of fine-grained continuous brightness records that could catch a possible megastructure in the act. With all this new data, astronomers faced a big task: to sift the cosmic haystack for a handful of really weird needles. Among the countless stars flickering in space, most showed regular, predictable dips due to passing planets or known types of variables. But every so often, a star would act up in ways that didn't match existing categories, opening the door again to the tantalizing question: is this star's weirdness caused by something natural we don't yet understand, or could it be a glimpse of technology at work among the stars? As decades passed, the search was also shaped by cultural changes and technological leaps outside astronomy. The field of data science exploded, providing fresh tools to analyze billions of data points at once, an absolute requirement if you're hunting for rare one-in-a-billion scenarios. Machine learning algorithms, taught to spot the strangest patterns among terabytes of telescope records, became critical. This approach meant that astronomers could look not just for the expected, but be alerted when something strange popped up. A crucial shift, because the first signs of an alien megastructure might look nothing like our initial guesses. Parallel to this, groups like SETI, the Search for Extraterrestrial Intelligence, widened their approach beyond listening for alien radio signals. Instead of limiting themselves to messages in a bottle sent across the stars, they began thinking about technosignatures, any artifact, glow, shadow, or temperature spike that could only be caused by advanced technology. Suddenly, finding a Dyson sphere or any other massive construction wasn't just a fun hypothetical. It became a central goal in the effort to detect intelligent life, adding enormous weight to the systematic search for signs that someone, somewhere, had remade their solar system in dramatic fashion. Over the last few decades, the hunt for alien megastructures benefited from improved worldwide cooperation. Major observatories started sharing their findings, cross-checking signals flagged as unusual, and pooling data from different types of sensors: visible, infrared, radio, even X-ray. This global collaboration meant that discoveries didn't live or die by one group's instruments or algorithms, but could be independently verified and tracked across multiple platforms. The more sensitive our tools got, and the more often we observed the same patches of sky, the better our odds of catching something truly exceptional. It's worth noting that the attitude of researchers generally stayed pragmatic, even as they chased what could be the ultimate sign of cosmic neighbours. They knew that for every 100 cases of strange starlight, 99 or more would turn out to be dust clouds, variable stars, instrumental glitches, or boring natural phenomena. Yet each time something really odd appeared, something that withstood wave after wave of natural explanation attempts, the excitement returned. The scientific process demanded that the alien hypothesis always be the last refuge after every other cause had been tested and eliminated. One important shift was recognizing that not all megastructure candidates would be obvious. Early ideas focused on stars suddenly dimming by huge amounts or sending out powerful bursts of energy at weird intervals. But as datasets grew and astronomers learned to read subtler clues, they expanded their thinking. Complex, irregular light curves, multiple levels of dimming, or stars with a permanent infrared glow without an obvious dust source became part of the catalogue of megastructure candidates. Astronomers honed their tools to differentiate between natural cycles, like star spots or eclipses, and the types of highly engineered changes an artificial construction might cause. Eventually, high-profile examples captured public attention and fueled popular interest in the search. Shocking news headlines sometimes exaggerated the findings, turning any oddball patch of sky into evidence for aliens. However, professional astronomers always kept the focus on measured curiosity, careful vetting, and the recognition that nature still has many surprises up its sleeve. In fact, as odd as some signals are, most have ultimately turned out to be complex, previously unknown types of variable stars, big clouds of fine dust, or collisions between objects in remote star systems. Every resolved puzzle deepened our catalogue of stellar phenomena, while still leaving room for that one truly impossible to explain case. Through all this, the search for alien megastructures matured from a fringe pursuit to a major scientific campaign. Today, entire survey missions periodically scan regions of the Milky Way and even other galaxies for signals that match the predicted fingerprints of cosmic engineering. While many cases go in the probably natural file, the methods get sharper with every new find. Astronomers have even created ranked lists of the most peculiar objects in the sky, allowing them to zero in on the best candidates for follow-up. The adventure of searching for alien megastructures is also a lesson in humility for planet Earth. The universe, after all, is nearly 14 billion years old and filled with billions of stars. If even a tiny fraction of advanced civilizations out there followed a similar technological path as ours, figuring out how to harvest starlight at scale, some evidence should eventually make itself known in the ways their stars behave. Every star is a potential clue, and every strange dimming is another lead to chase down. At the same time, we're still learning about stars themselves and the bizarre tricks they can play. The more we uncover about natural astrophysical processes, the clearer it becomes just how challenging the search is. From complex magnetic cycles to never-seen-before types of interstellar dust clouds, the universe is richer in unexplained phenomena than anyone expected. In chasing alien megastructures, we've grown our understanding of stars, planets, and cosmic chemistry by leaps and bounds. Now, with next-generation instruments like the James Webb Space Telescope coming online, and with increasingly powerful telescopes under construction around the world, the hunt is entering a new chapter. These machines bring higher sensitivity across a wide range of light types, visible, infrared, and beyond, making it possible to examine known candidates in greater detail and discover whole new sets of oddballs. And as astronomers continue to refine their models of what megastructures could be, every observation, every pass across a star-studded sky is a chance for curiosity, skepticism, and maybe, just maybe, the ultimate cosmic discovery. The search for alien megastructures, then, is a story of expanding possibility. It began as a theoretical exercise, a playful what-if, but is now central to our exploration of the universe. From the early speculations of brilliant minds like Freeman Dyson to the present-day teamwork of global observatories and computer software, we keep pressing forward, guided by data, careful analysis, and a persistent hope that one of those billions of blinking lights might finally reveal the unmistakable hand of intelligence at work. And through all this, as new discoveries stack up and new anomalies appear in the night sky, one fundamental question keeps echoing. If we really do find something, where should we look next? What would you think if astronomers suddenly noticed a star whose light dips and brightens in ways that all our current scientific explanations cannot fully account for? This is exactly how the story of Tabby's star, also catalogued as KIC 8462852, gripped both the astronomical community and the general public. The first unusual observations happened back in year 2009, when the Kepler Space Telescope began its systematic hunt for exoplanets. Kepler monitored over 150,000 stars, waiting for signs of dimming that would suggest a planet was passing in front of its parent star. But among this sea of data, the signal from Tabby's star looked different right from the start. The star's light did not simply dip a little bit now and then, the way it might if a planet of predictable size and orbit crossed its face. Instead, astronomers noticed wild changes. Sometimes, starlight decreased by a small amount, as you would expect with a big Jupiter-like planet. At other times, though, the drop was far more extreme. Up to 22% of total light vanished, which is about 10 or even 100 times bigger than what most exoplanet transits cause. These dips did not happen on a regular schedule. They were irregular, lasting anywhere from a day or two to nearly a week, and didn't line up with any repeating pattern. Years went by as the data rolled in, showing that Tabby's star was unpredictable, odd, and apparently unique among all the other stars Kepler observed. As astronomers dove into the data, they found even more strange details. The dips in brightness came in all shapes and depths, with clustered events and then long periods of normal light. No other star in the Kepler mission study area acted in such a baffling, chaotic way. At first, the variability looked almost random, but later, analyses revealed some partial clustering and trends over months or years. Added to this, there were hints of a longer-term gradual decrease in the star's overall brightness, at least over the 4 years that Kepler observed it. No known family of stars, planetary systems, or natural phenomena fit this profile, especially with such drastic, irregular drops. A critical figure in bringing attention to Tabby's star was Dr. Tabitha Boyajian, an astronomer at Yale University. She and her colleagues noticed the pattern while conducting a citizen science project called Planet Hunters, which let people browse Kepler data to spot potential planets. When the team first saw the odd light curve, they double-checked everything for instrument errors or processing glitches. Once these possibilities were ruled out, the uniqueness of this star stood out immediately. Over the next few years, the team published several papers laying out the raw data, the weirdness of the dips, and the first round of scientific guesses about what might be going on. A big part of understanding Tabby's star comes down to how astronomers explain changing starlight. Most of the time, dips in light from a star are predictable. If planets orbit a star, they block a tiny part of the light as seen from Earth, and this pattern repeats every orbit. In tight star systems, eclipsing binaries create more complicated but still rhythmic patterns. Gas or dust often impact light, but even then, the change is regular, or at least shows a clear cycle. Tabby's star broke all of these patterns. The only thing that stood out was how inconsistent and deep the dimming events were. When it came time to search for explanations, scientists took the problem seriously and laid out a list of possible natural causes. The first idea was a massive swarm of comets, or perhaps a huge ring of debris left from some ancient planetary collision. This swarm would have to be both vast in number and uneven in position, perhaps breaking apart and reforming in new shapes over time to cause the strange dips in starlight. There's some theoretical support for this. We know our own solar system has a cloud of debris and icy bodies orbiting far from the Sun, and other exoplanet systems can be just as chaotic. Still, the numbers required were staggering. You would need hundreds, perhaps thousands, of giant icy bodies, all coincidentally passing in front of the star at weird intervals, to pull off the dips seen in the Kepler data. Another possibility was a cloud of interstellar dust, drifting through space between Earth and Tabby's star, partially blocking its light and changing as the cloud moved. But when astronomers examined the light in different color ranges, they noticed that the dips looked grey, meaning all colors of visible light dimmed roughly equally. Interstellar dust, by contrast, tends to block blue light more than red, creating a telltale color fingerprint. The more closely astronomers looked, the less likely this explanation became. Other ideas tried to rely on problems with the star itself. Maybe Tabby's star was a weird type of variable star, a sun that changes brightness for reasons we just do not understand yet. Variable stars usually show repeating cycles as they swell and cool over days, weeks, or even years. But this star is an F-type main sequence sun, more or less like our own, and does not fit with any known category of variable. Its overall output of heat and light, as well as its spectrum, appeared stable and normal aside from those sudden, wild dips. All kinds of natural explanations were weighed. One suggested that a planet with a huge system of rings, like Saturn's rings, but much, much bigger, passed in front of the star, covering a large fraction of its face. but modelling showed that you would need rings orders of magnitude larger and more chaotic than any seen in our solar system, which again seemed less and less likely. Other researchers suggested planetary debris may be left behind from the destruction of a planet or moon, but the timing and size of the dimming events did not match models based on gravitational dynamics. Given the lack of convincing natural causes, it was almost inevitable that the conversation would turn toward more speculative ideas. The question emerged, what if the dimming events were not a result of random dust or debris, but of giant artificial constructs? This is where the idea of alien megastructures came back into play. Specifically, scientists considered whether what we were seeing was the signature of a Dyson swarm, a collection of huge solar energy collectors or other structures, built by an advanced civilization to harvest energy from their star. The scenario went as follows. Imagine thousands or millions of objects on different orbits around Tabby's star, each partially blocking its light at unpredictable intervals. If these objects had irregular shapes, moved on unpredictable paths, or changed over time as they were built, repaired, or destroyed, their collective shadow could mimic the strange, extreme dips that astronomers observed. While this possibility got a lot of public attention, most scientists remained cautious, explaining that this theory is a last resort, used only if all natural explanations are exhausted. Still, the numbers were exciting to think about. Very few natural objects can dim a star by over 20%, except in eclipsing binaries, so something really big or widespread had to be present in the system. The buzz about alien megastructures, combined with the oddness of the dips, led to a surge of follow-up studies using both ground-based telescopes and other space observatories. Researchers looked for other clues, including whether Tabby's star emits additional energy in other parts of the spectrum, such as infrared or radio. The logic is simple. If some of the star's light was being captured and used by huge megastructures, some of that energy might be re-emitted as waste heat, visible to us as excess infrared light. Careful surveys showed no clear sign of extra infrared from Tabby's star, which made the megastructure scenario less likely but not impossible. It just meant that if any technology was present, it would have to be advanced enough to channel or hide its waste heat more efficiently than anything we can imagine. Another kind of search focused on possible radio transmissions that might indicate intelligent life. The SETI Institute pointed powerful radio dishes toward Tabby's star, listening for transmissions or signs of technology. Over months and years, these radio searches produced no signal out of the ordinary. Again, this neither proved nor ruled out the presence of aliens. It just closed off one more potential window where evidence could have appeared. With every new year, astronomers added more data to the pile. The pattern of irregular dimming continued, but new observations also found that the overall brightness of Tabby's star had faded by a tiny amount, less than 1%, over the span of a century if older photographic records were included. Some scientists argued that the historical data didn't match the newer space telescope measurements perfectly, and issues with old photographic methods could have skewed the results. The controversy even turned into a small drama as teams debated the accuracy of century-old astronomy plates and compared them to digital records. Worldwide amateur astronomers got involved too. As news about Tabby's star spread, enthusiasts all over the globe pointed home telescopes at the distant star, hoping to catch their own record of one of those rare, mysterious drops in brightness. Their data helped fill in gaps between the big observatory visits, sometimes catching new dimming events in near real time. This citizen science effort kept the mystery alive and ensured that Tabby's star remained under constant surveillance, despite all the professional resources being pulled in different directions. Since the original Kepler observations, other telescopes like Spitzer in the infrared and ground-based facilities using various filters have re-examined Tabby's star. Occasionally, a new set of dips would pop up, always different in timing and depth, confirming that the irregular dimming is an ongoing feature of the star rather than a one-off event. These multi-wavelength studies also reinforced some patterns. Whenever the star dipped, the dimming was similar across both red and blue light. That reinforced the notion that, whatever is blocking the light, it is made of bigger particles, because smaller dust would selectively block blue more than red. Despite all these efforts, scientists still haven't reached a firm answer about what's causing the light curve drama at Tabby's star. As the years went on, the community leaned more towards circumstellar dust that behaves outside the models we currently use, maybe generated by the breakup of comets or by processes we haven't actually observed elsewhere yet. A popular proposal is that superfine dust produced by evaporating, colliding, or disintegrating bodies orbits the star on unpredictable paths. Because this dust is more clumpy and persists for only short stretches of time, it would explain why dips come and go, never matching up neatly. Yet here, too, questions remain. The amount, composition, and clumping of such dust would have to be just right. If even a little bit changed, the light curve would not match observations. Other astronomers believe we may eventually find an odd new type of variability within stars like Tabby's, though as yet there is no physical model that predicts such behavior for this type of main sequence star. Some more speculative minds consider that gravitational effects from an unseen companion star or even a small group of brown dwarfs, a kind of failed star too small to fuse hydrogen, could be tossing dust or debris through the system at intervals. Yet no clear evidence of a binary companion or nearby brown dwarfs has been picked up in the most thorough scans. Throughout all this, one thing is clear. Tabby's star set a new standard for what counts as an anomaly in the search for alien megastructures. Before this case, most megastructure hunting was hypothetical or based on looking for subtle clues in huge databases. Here, astronomers were looking at a real object in real time, where the puzzle was deep enough to defy easy categorization and, at least for a while, left the door open for ideas from the cutting edge to science fiction. The mystery energized more than just the direct followers of Tabby's star. Because the dips were so dramatic and the possible explanations so varied, the entire field of exoplanet hunting benefited. Astronomers adopted new strategies and improved tools for modeling both normal and strange brightness changes. The case drove home the importance of continuous monitoring, crowdsourced science, and sharing data between professional and amateur channels. In practical terms, this meant more complete records, better models, quicker responses to new events, and an openness to a wider range of phenomena than before. This process, the search for an answer, is ongoing. As of today, Tabby's star still flickers unpredictably, and while dust is the leading explanation, no theory fits every single fact about the brightness changes. The case has been featured in newspapers, podcasts, and countless scientific papers, always highlighting both the excitement and the challenge of unraveling nature's secrets. The debates around Tabby's star have been mostly calm, highlighting a healthy mixture of skepticism and fascination. Scientists occasionally revisit the issue of artificial structures, but the focus remains on careful, evidence-driven thinking. Even without a dramatic discovery at Tabby's star, the episode has changed how we look at the universe. It has prompted a re-evaluation of what is possible around other stars and how we interpret unexplained signals in astronomical data. The community now recognizes that there are probably many more stars like Tabby's out there, hiding among the billions waiting to be surveyed more closely. By keeping techniques sharp and attitudes open, even while demanding rigorous evidence, astronomers are prepared for whatever new puzzles the sky throws their way. Every night, telescopes of all sizes turn toward Tabby's star, ready to record its next unexpected flicker. The drive to solve the mystery has deepened interest in stellar astrophysics, boosted awareness of the challenges of interpreting strange data, and fostered a vibrant partnership between professional and amateur sky watchers. The legacy of Tabby's star will most likely be its role as a benchmark for cosmic oddities, a clear reminder that sometimes the universe refuses to fit into neat categories. Thus, the search continues, charting a path through the unknown, illuminated by the persistent, unpredictable, and still unsolved glow of Tabby's star. After spending so much time wrestling with the mysteries of Tabby's star, it's only natural to start thinking about the extreme possibilities that might lurk behind such strange observations. One of the wildest ideas, for many scientists and sci-fi fans alike, is the prospect that advanced civilizations could build what's known as a Dyson sphere. This is not just another cool science fiction gadget. The story of the Dyson sphere starts with a genuine scientific proposal that has grown into one of the central concepts for thinking about how truly advanced technological societies might try to satisfy their colossal energy needs. To really get a grip on why the Dyson sphere fascinates astronomers and dreamers alike, you have to go back to the year 1960. That year, the British-American physicist Freeman Dyson published a now famous paper in the magazine Science. He raised a pretty blunt question. If technological civilization keeps growing and using more and more energy, wouldn't there come a point where a planet's resources just aren't enough? So what's the next level? Dyson argued that a truly future-facing civilization would want to capture as much energy as possible from its home star, not just what lands naturally on a planet's surface. To do that, they'd need to actually build structures in space by gathering material from planets, asteroids, and moons, and set up collectors to grab the lion's share of their star's radiation. What Dyson imagined, technically, is called a shell, or swarm, surrounding a star. The most familiar sci-fi version is a solid shell, a huge, uninterrupted bubble encasing a sun, but Dyson himself, and later astronomers, emphasized that this complete shell is probably impossible because of sheer engineering headaches like stability and gravity. Instead, they proposed a swarm, trillions of separate satellites or panels moving in orbit, each grabbing a bit of sunlight and converting it into useful energy. Whether as a full sphere, a series of rings, or a cloud of collectors, the result is an artificial construction on a truly insane scale. Why does it matter? In our current technological stage, humans rely on power from fossil fuels, the wind, ocean waves, a bit of geothermal heat, and some solar power. But all these sources together are nothing compared to the energy our sun spits out every second. If a civilization wants to build giant machines, run endless computers, and maybe travel between stars, it needs more juice than a single planet collects. Spheres or swarms encasing stars would be the logical next step for a society wanting to step beyond planetary limits. That's the theory part, but in practical terms, it serves as a signal for how alien civilizations far ahead of us might leave detectable fingerprints. Astronomers figure that if aliens did build enormous light-capturing structures, there would be telltale signs visible to us even from thousands of light-years away. First, by blocking or redirecting a star's light, those megastructures can create unique dimming events, sort of like what was seen at Tabby's star, although Dyson's ideas suggest an even more pronounced, possibly steadier effect. Second, because energy is never perfectly recycled, you'd expect waste heat to be radiated away, probably as infrared light. The combination of sharp dips in visible light and an unexplained rise in infrared would become massive clues pointing to artificial activity. Let's also talk about the physical scale we're dealing with. The Sun, for instance, puts out about 386 billion megawatts every second. Imagine harnessing just a fraction of that. To construct even a partial Dyson swarm for our own star, you'd need to mine entire planets or asteroids for materials and go through levels of engineering complexity that our most demanding space programs can't currently touch. Even so, astronomers argue that with enough time, self-replicating machines or highly organized construction technologies could, in theory, piece together a swarm over thousands or millions of years. The crucial point is that once such swarms are in place, the star starts looking stranger than anything we're used to, from strange light curves to excess heat emissions. The Dyson sphere wasn't just a theoretical exercise, though. It shaped the direction of the search for extraterrestrial intelligence in actual, practical ways. Whereas the early SETI programs focused mainly on catching radio waves, a sort of cosmic phone call, researchers interested in megastructures shifted part of their search toward observing light curves, hunting for unexpected dimming, and scouring the skies for those weird heat signatures that might imply massive technological construction. Surveys were set up using telescopes that could measure not just visible light, but also the infrared radiation that a functioning Dyson sphere would pump out into the cold of space. Through the 1970s and 1980s, the idea got more scientific teeth. Researchers began to model what different versions of Dyson spheres might look like when observed from Earth. Some proposed that incomplete swarms, maybe just a few % coverage of the star, would mimic certain types of natural debris disks, but with telltale physical differences. Others explored what multi-star systems would look like if more than one sun was encased by swarms. Soon, astronomers realized they had to be careful to distinguish between artificial megastructures and naturally occurring things like thick rings of dust or recently formed planetary systems. By the time sky surveys started capturing huge slices of the galaxy in detail, Dyson spheres and related concepts became a real part of the cataloguing process. Astronomers began flagging stars with weird brightness dips, particularly those with repeated or irregular patterns that don't match ordinary planets or star spots. They also hunted for stars with an unexplained overabundance of infrared light, suspecting these might represent energy being turned into waste heat at a scale beyond what natural processes tend to produce. These infrared excess objects are unusual and worth a closer look. but so far they all have natural explanations. Thick, rubbery dust disks, clouds of gas, or young stars still wrapped in the leftovers from their formation. But even if a true Dyson sphere has never been found, the theory keeps paying dividends. As technology advances and telescopes become more precise, astronomers keep re-evaluating possible candidates. Every new generation of space telescope has higher resolution detectors for both visible and infrared light, making the search more sensitive and more comprehensive. Algorithms that flag odd patterns are refined year after year. Dozens, sometimes hundreds of stars are earmarked every few years for follow-up, simply because their light curves or their color signals look just off enough to merit closer inspection. The concept has also sparked a steady stream of creative proposals about what forms alien engineering might take. Some suggest that instead of spheres, advanced societies might build rings, arcs, or swarms designed around specific needs and available materials. Others imagine clusters of space habitats or mega-satellites, each optimized for a unique environment or energy source. More radical ideas include interstellar versions, spheres built around more exotic types of stars, or even around black holes for the ultimate in energy density. On Earth, the Dyson sphere has become something of a shorthand among researchers for any sign of truly industrial-scale star harvesting activity. You'll often see Dyson signature as a shortcut for the unique astronomical fingerprints associated with big artificial light collectors. This is helpful for researchers issuing reports, cataloguing unusual stars, and brainstorming about the types of techno-signatures we might someday spot. One thing to keep in mind is the immense risk of misinterpreting data. For every promising blip, astronomers must run through the checklist. Could interstellar dust clouds create a similar effect? Could a star surrounded by comets or gas from a violent collision make the dimming or infrared bump we observe? Does the light curve match any new or exotic class of star we're just learning about? This is why teams spend endless months ruling out possible dust, variable stars, instrumental errors, and all other natural interpretations before even mentioning the possibility of artificial structures. In every case so far, natural explanations have taken precedence, but the ongoing collection of new data always leaves the door ajar for surprise. It is important not to forget what a Dyson sphere would mean for our understanding of technology and time. If one ever were confirmed, the civilization behind it would need to have mastered not just local planetary resource management, but also enormous-scale mining, logistics, and construction spread over thousands or even millions of years. It signals a leap from planetary to stellar engineering, indicating a species that has avoided self-destruction and managed to coordinate projects on the grandest imaginable stage. Tools for seeking out these colossal objects keep getting sharper. Missions like the Wide Field Infrared Survey Explorer, which launched in the year 2009, were designed to map the sky for faint sources of infrared light that might come from waste heat produced by technologically active populations. As computers become more powerful, researchers run ever larger simulations of all the ways a Dyson swarm could dim or reroute a star's energy into wavelengths we could detect. They even mix in lessons from major anomalies like Tabby's star, constantly updating their templates for what to look for next. Despite decades of searching, no star has yet screamed Dyson sphere without any doubt. But the ongoing absence of evidence does not prove that these megastructures do not exist. It may just mean that we need better instruments, more sophisticated scanning patterns, or a shift in what patterns we expect. Some believe that advanced civilizations may build structures that are optimized to not be seen, or which channel energy in ways our physics does not yet anticipate, making them effectively invisible to our surveys. The interest in the Dyson sphere concept is not limited to academic astronomers. Popular books, television series, and movies keep the idea alive in culture. Even casual sky watchers may keep half an eye open for those rare stars with suspicious light curves, often inspired by the original work of Dyson and his successors. The cross-pollination between science and imagination means new ideas filter back into research, with even the wildest science fiction sometimes inspiring a new angle in scientific surveys. Some current projects aim to search whole galaxies at once for infrared emissions at levels consistent with industrial-level activity on a huge scale. The idea is to catch not just individual stars but any region showing heat that cannot be matched by what's visible in ordinary light. These panoramic analyses could reveal anything from faint clusters of partial swarms to signs of galaxy-spanning engineering efforts that we can barely begin to model. With each new wave of data, the hunt becomes more nuanced. Whereas early efforts searched for a perfect shell completely masking a sun, more recent studies look for patchy, moving, or evolving swarms, recognizing that even advanced alien civilizations are likely to build in stages, adapt designs, and cope with accidents or wear and tear. The search now covers not only steady-state signs, but temporary events, like sudden bursts of construction or the accidental destruction of a big hunk of a swarm. As for what we might see, almost every angle is considered. Theoretical researchers have calculated how much light would leak from between swarm components, how much starlight might be reflected back into space rather than absorbed, and how much time it would take for a galaxy full of civilizations to fill out swarms around their stars. The numbers are always huge, measured in hundreds of thousands, millions, or even billions of years. But from the standpoint of cosmic evolution, these are not impossible timescales. Addressing the sometimes fragile boundary between enthusiasm and evidence, scientists maintain routines that keep the field from leaping ahead of the data. When an object looks promising, they commission follow-up observations, compare multiple wavelengths, double-check light curves, and review all known databases for other similar cases. This careful approach prevents the field from burning out on false alarms and hones in on the next set of anomalies most deserving of attention. Looking to the future, astronomers are eyeing new infrared instruments, collaborations between observatories around the globe, and ambitious digital sky surveys, producing unimaginable quantities of data ripe for machine learning and pattern hunting software. The dream is that one day a signal will emerge that is so regular, stable, and out of step with every known star or dust effect. The only reasonable answer left will be complex, engineered structures of the sort Dyson described over 60 years ago. Until that day, the scientific and technological imagination will keep turning. Every discovery of a strange star, odd light curve, or unexplained excess of heat sparks a fresh round of proposals and ideas, pushing both theory and observation forward. Behind all of this is the desire to answer whether humanity is truly unique as a technological civilization, or whether the signs of engineering can be found, at last, among the ancient lights of the cosmos. Now, as conversations about Dyson spheres keep growing and theories about what advanced civilizations might construct become an active part of astronomical research, it makes sense to ask how scientists actually rank civilization advancement. This is where the Kardashev scale comes in and changes the game. The scale itself popped into scientific discussion back in the year 1964, when Soviet radio astronomer Nikolai Kardashev came up with an idea that was at once simple and absolutely ambitious. Measure technological progress based on the total amount of energy a civilization can consume and manage. Rather than looking at technology type or cultural traits, the Kardashev scale focuses on pure energy mastery, a straightforward metric that researchers could in principle look for in real astronomical data. Kardashev suggested that as societies progress, they move through categories according to the scope of resources they can command. The simplest version splits the ladder into 3 rungs: Type 1, Type 2, and Type 3. Type 1, civilizations can harness all the available energy on their home planet. Type 2 has figured out how to tap into the full output of its star. Type 3, meanwhile, controls energy on the scale of an entire galaxy. To put numbers on it, think of a Type 1, the planetary society, as using about 10 to the power of 16 watts, which is the maximum energy available from sunlight, wind, oceans, volcanoes, and all other geophysical systems on Earth. A Type 2, the stellar civilization, would have to exploit something like 10 to the power of 26 watts, which is the entire rotational and nuclear output of a sun-like star. Type 3 is on another order of magnitude altogether, at 10 to the power of 36 watts, the sum of energy produced by a large galaxy like the Milky Way. Where do humans stand on this ladder? This gets debated every year as data about global energy use comes in. By most estimates, modern Earth sits at about 0.7 on the Kardashev scale, not even at Type 1 yet. Our global energy use is measured in the tens of terawatts, far below the mark needed to control even the planet's full resources, let alone those of an entire star. We harness small fractions of wind, water, petroleum, solar, and nuclear power. Most of the sun's energy hitting Earth is still absorbed by the environment or radiated back into space. What's interesting is that worldwide, human energy consumption has climbed from roughly 1,000th of the planetary total several centuries ago to its current position, implying steady progress. But the leap to even a full Type 1 will require new sources or radical changes in technology. The scale is useful in more ways than just classifying our progress. Because the steps are huge, each jump upward demands machinery and infrastructure that leave traces beyond their homeworld. If a civilization ever does reach Type 2 and starts engineering on a stellar scale, the effects could light up whole solar systems in ways we could see from light years away. Dyson spheres or swarms are a direct example of this kind of transition. When a society starts building big, bright, and hot structures to bottle up stellar energy, they create signatures. Waste heat, strange light curves, possibly intense engineered radio emissions that could be picked up by powerful telescopes. Type 3, stretching over a galaxy, would push this all the way. Kardashev's original scale was meant to guide the search for intelligent life in the universe, especially when it comes to using radio waves to signal across cosmic distances. He thought that detecting truly giant civilizations would only be possible if they manipulated quantities of energy massive enough to make them stand out from natural backgrounds. This informed early SETI thinking: where to point the antenna dishes, what frequencies to monitor, how to interpret the most energetic galactic phenomena. With the scale in mind, SETI researchers imagined that megastructures, energy bursts, or even signs of large-scale mining or construction might show up in cosmic surveys if a civilization had reached higher types. Over the decades, scientists and theorists have adjusted the Kardashev scale by filling in fractional values and specifying what it might mean to be at 0.5 or 1.8 of the journey. They have debated whether new types should be added beyond Type 3. Perhaps civilizations could tap the energy of entire galaxy clusters, or even manipulate dark energy, black holes, or previously untapped cosmic resources. Each suggestion is about pushing boundaries, but the original 3 steps remain the core framework because of their grounding in astronomical physics and observable effects. For those looking for alien megastructures, the Kardashev scale is not just a thought experiment but a practical filter. A discovery like a Dyson sphere would strongly suggest a system at the Type 2 stage. Astronomers keep this in mind whenever a star shows any of the techno-signatures explored earlier: waste heat at the wrong wavelengths, abrupt or repeated dimming, or odd radio emissions. The scale provides a reference point for the level of engineering required. It also tells us what sorts of cosmic environments might make the best hunting grounds for evidence of non-natural activity. When researchers analyze sky survey data, they can assess whether anomalies fit what we'd expect from Type 1, 2, or even 3 civilizational activity. For instance, if a star is dimming regularly, but without showing significant extra infrared, it might mean a natural dust cloud. If there's intense heat coming from an invisible source, it's worth checking if the energy matches what a Dyson swarm might generate. If a whole region of a galaxy glows in the infrared in sync, but doesn't match the number of young stars, it could, in theory, point to galaxy-scale engineering on a Type 3 level. These patterns have given astronomers a kind of cosmic roadmap. Younger solar systems packed with planets and debris are often studied for evidence of Type 1 or early Type 2 traits, things like artificial satellites, energy collectors, or orbital engineering projects. Old, dense regions closer to galactic centers offer possibilities for larger, sustained megastructures and possible Type 2 or 3 traces. Scientists even speculate about civilizations that could run networks of Dyson spheres or megastructures, coordinating across several star systems. In everyday terms, what sets the Kardashev scale apart from other sci-fi ideas or older methods of classifying advanced societies is that it pulls the conversation away from personalities or specific cultural achievements and drills down to raw, measurable power. It strips away softer variables and focuses on what's likely to be noticeable even for astronomers far away: the rerouting of planetary, stellar, or galactic energy, and all the technological spillover that comes with such actions. Of course, the practical side of the search comes with a dose of skepticism. For decades, teams have flagged odd radio bursts, unexpected energy surges, and various starlight dimmings. Most end up tied to natural phenomena: colliding neutron stars, young galaxies, special classes of variable stars, or exotic but still unplanned explosions and events. The scale provides context, and when a real anomaly persists after everything else is eliminated, the possibility of seeing a new rung on the cosmic ladder gets considered carefully and rigorously. Because the scale is about energy, it also puts natural constraints on how societies evolve. To move up, a civilization must not only use more energy, but also learn to channel it safely, avoid environmental collapse, and perhaps invent entirely new forms of storage, transmission, and recycling. This has replaced some of the naive optimism in older science fiction with serious debates over risks, engineering limits, and the unknown physics that might shape our future, as well as that of any hypothetical exo-civilization. An interesting offshoot is how the Kardashev scale forces people to think about waste and inefficiency. No process is perfect, and as civilizations use more energy, more gets lost as byproducts, mostly as heat. By the time you reach Type 2 levels, so much starlight or other forms of energy are captured and redirected that the surrounding system warms up, sometimes dramatically. Telescopes can search for this extra warmth, creating a bridge between theory and observation. The more advanced the civilization, the more waste it leaves in terms of stray photons or random signals detectable over astronomical distances. The framework also affects how funding agencies and mission planners set priorities. Big projects like the Wide Field Infrared Survey Explorer or the upcoming generations of sky mapping satellites are guided by questions rooted in the Kardashev scale. Astronomers allocate precious telescope time to promising sectors of the sky where high energy signatures or large megastructures might be easier to spot. By focusing on scale and the physics of heat and light, these research programs get more precise and productive. When you see news headlines about alien megastructure candidates or unexplained signals from deep space, chances are the data is being measured, at least partly, in terms of the Kardashev scale. The scale encourages reporting in raw, comparative terms. How much more energy is involved than in natural processes? Is it a planetary, stellar, or galactic signal? How does it compare to our own energy footprint or the output of a familiar star like the Sun? These comparisons make the search for extraterrestrial intelligence both practical and grounded, anchoring it in numbers anyone with a solid science background can check and recalibrate. There's a social edge to the popularity of the Kardashev scale that goes beyond just science. People use it to talk about the future of human civilization, to plan for energy needs, and to debate what kinds of environmental, political, or technological challenges might lie ahead if we ever try to harness Earth's full power. Historians and writers point to big leaps in technology, like the steam engine, electricity, nuclear fission, and now solar panels and battery technologies, as early indicators that we might someday inch up the scale. In academic and public settings, it's common to use the fractional position of humanity to underscore both how far we've come and how much is left to be discovered. In the world of research, the scale is often a springboard for more detailed thinking about how actual searches should be designed, which anomalies should get the most scrutiny, and what kinds of data are most trustworthy. If researchers are weighing whether a strange radio burst, mysterious light dip, or big patch of unexplained heat is a sign of life, the Kardashev metric helps to rule out low-level natural noise and prioritize phenomena that truly leap out against the cosmic background. That does not mean the scale is without controversy or challenges. For example, some have argued that truly advanced civilizations might be far more energy efficient, using less power for greater effect, recycling waste heat with perfect precision, or even hiding their activity to avoid interference or detection. Others point out that the universe is filled with unpredictable events, supernovae, black hole accretion disks, or gamma-ray bursts that can temporarily mimic the megastructures or energy surpluses predicted by the scale. This pushes astronomers to sharpen their definitions, re-examine models, and stay on guard for new classes of both natural and artificial phenomena. Recently, computer models and machine learning have entered the field, helping to classify huge samples of stars and galaxies according to their energy signatures and spectral fingerprints. By scaling up, engineers can now use Kardashev's logic to search enormous sky patches for anything that matches patterns of planetary, stellar, or galactic engineering. When something anomalous turns up, software is used to compare it against literally millions of known stars and galaxies, helping to filter out red herrings and point the way toward the next big lead. There's also growing interest in building new variations of the scale, including ones that address other potential hallmarks of civilization beyond energy. Some researchers want to incorporate control of matter, mastery of computation or bioengineering, or even dominance of subatomic forces. But energy remains the universal language of space. Photons, heat, radio signals, and gravitational signatures are what actually travel between stars and what our telescopes are best at detecting. The growing reach of the scale shows up in interdisciplinary projects. Astrobiologists, planetary scientists, engineers, and even philosophers use it as a way of thinking about the range of possibilities for life in space. When they talk about what forms alien civilization might take, they invoke the Kardashev scale to add realism and a sense of boundaries. It helps frame debates over where to look, what technologies or signals we might recognize, and what surprises could lie beyond even our best theories today. Looking at the wider impact, the Kardashev scale has become a tool to help us keep our ambitions grounded in the realities of physics and what's observable. Instead of just imagining far-off civilizations, the scale challenges astronomers to produce evidence at each new rung of advancement and to explain how such activity would physically manifest itself to observers back on Earth. This means a relentless focus on data, on predictive models, and on learning new ways to spot where nature ends and engineering might begin. Every attempt to find signs of alien life using the Kardashev scale is a push to balance skepticism with open-minded searching. Teams cautioned by past mistakes and failed leads are more careful than ever about putting new discoveries in their proper context. At the same time, the scale drives invention, new sensors, more sensitive measurements, and creative collaborations between research centers. The questions it poses spark curiosity, technical progress, and international cooperation as astronomers and engineers piece together the puzzle of cosmic life. The next time you hear about strange cosmic signals, mysterious dimmings, or energy surpluses in star systems or galaxies, remember that behind all these searches is the relentless logic of the Kardashev scale. It quietly underpins which projects get funded, what resources astronomers devote to deep sky surveys, and how the best minds interpret ambiguous or surprising phenomena. By tying everything back to the hard facts of how much energy a society uses and what traces that use leaves in the sky, the Kardashev scale keeps our search for cosmic neighbors both imaginative and squarely based in observable science. As discussions about the Kardashev scale make clear, the key to looking for technologically advanced civilizations is searching for structures and projects that would change a star system on a massive scale. While Dyson spheres are the most well-known example, researchers and science fiction writers have spent decades coming up with alternative megastructures that advanced societies might want to build. In particular, ring worlds and stellar rings stand out as compelling ideas that blend big-picture engineering with scientific plausibility. These projects stretch the imagination of what a civilization could accomplish, but they are also useful because they help astronomers know what sorts of unusual signals and light patterns to look for. Ring worlds became famous outside the boundaries of pure science thanks to Larry Niven's novel Ringworld, published in the year 1970. In his story, an advanced civilization constructs a gigantic ring encircling a star at a radius roughly equal to that of Earth's distance from the Sun. The structure is so large that if you could stand on it, the inner surface would look like a planet that wraps in a circle, with the star always present directly overhead. Niven calculated that his ring world would have a radius of about 150 million kilometers, the same distance as Earth's orbit, creating a circle with nearly 1 billion kilometers around. The sheer scale is hard to picture, but what matters for astronomy is that, unlike a cloud or shell, a ring blocks only a specific thin band of light from its parent star. The basic physics of a ring world start with the idea of maximizing usable real estate and sunlight. Instead of occupying a small rocky planet, inhabitants could spread out along a band millions of kilometers long. Engineers imagined such a ring could be built from the dismantled mass of planets, moons, and asteroids, using advanced materials strong enough to survive the stresses of orbit. If placed at the right distance, a ring would retain the perfect amount of heat for life, just as Earth does. Its rotation could provide artificial gravity, making life inside broadly similar to life on a planet. The concept itself is an engineering fantasy for humans right now, but scientists consider what signs it might create in astronomical data. When astronomers think about how a ring world would affect the way we see a star, the first thing that jumps out is its shadow. Unlike a Dyson sphere, which would diminish a star's overall brightness evenly or in a patchy way, a ring world would lead to precise, sharp dimming at particular times. If the ring is tilted with respect to our line of sight, we might see regular, sudden changes in brightness as the ring blocks some or almost all of the star's light. If the ring is edge on to us, we might see deep dips whenever it crosses between us and the star. These dips would be sharply defined, not gradual, and could last for hours or days, depending on the width of the ring and the speed of its orbit. Stellar rings are a related but different idea. While a ring world is designed specifically for habitation or energy capture, a stellar ring might just be a massive array of solar collectors, satellites, or unfinished construction stretching partially or fully around a star's equator. This could be an intermediate step for a civilization transitioning toward a Dyson swarm, a gradual process where more and more satellites are deployed until eventually the ring or disk fills out into a full shell. Like ring worlds, stellar rings would cast distinctive shadows, but they could also reflect light or radiate waste heat, and the vast numbers of components could produce complicated dimming patterns. Astronomically, distinguishing a ring world or a stellar ring from a natural ring of debris is one of the main challenges. Our own solar system, for example, has the asteroid belt and the rings of Saturn, beautiful, natural structures created over millions or billions of years by gravity and collisions. So, what makes an artificial ring stand out? Researchers point to regularity, abruptness of shadow edges, and repeated timing. If a ring crosses a star at predictable, clockwork intervals and absorbs light extremely efficiently without the scattering or fuzzy shadows seen in natural dust that could hint at something artificial. Also, an artificial ring might have features that don't fit natural explanations like gaps, patterns, or unusual reflectivity across different wavelengths. Astronomers and modelers have used computer simulations to predict what kinds of transit signals would be expected from large-scale rings. Ordinary exoplanet transits tend to have smooth, rounded dips in brightness as the planet's disk blocks a small patch of the star's light and then moves on. But a ring, especially a broad one, can cause an unusually long and very flat drop, sometimes with abrupt entry and exit edges. Models also show that if the ring is not a full circle, say an arc or series of linked segments, the resulting light curves would look even stranger, with multiple quick dips or complex step-like patterns as different segments block light in turn. Analysts use these predictions to screen star survey data for anything that looks off from the usual planetary rhythm. Some targets have intrigued astronomers in precisely this way. There have been a handful of stars, though not widely publicized for alien speculation, where the dimming curves suggest the passage of something wider or stranger than an ordinary planet. In many cases, dust rings, exoplanetary debris, or larger than average X-rings turn out to be plausible explanations. Still, astronomers always flag any candidate with extremely regular, flat, or abrupt light curve drops for further investigation, especially if repeated events match each time the ring completes an orbit. A key feature of these concepts is versatility. Unlike a Dyson sphere, which might be considered the endpoint of stellar development, a ring or partial ring could be built bit by bit. An advanced civilization could start with a thin ring and gradually widen it over centuries, generations, or millennia. Maybe the initial purpose is to maximize energy capture on a particular orbital path. Later, as technology grows, more material is added, perhaps for habitation, agriculture, or as platforms for telecommunications and industry. Each added segment changes the light-blocking pattern, meaning that continued observation of mysterious dimmings could, in theory, reveal a structure under expansion or repair. Beyond the straightforward engineering, the science gets more detailed when you consider reflectivity, waste heat, and spectral fingerprints. A ring of metal, polymers, or other synthetic materials would reflect starlight differently from dust or ice. It might only block visible light or reflect it in a way that would change the colors we see. In addition, artificial rings built for collecting solar energy would get hot. That heat would be radiated away as infrared. Depending on their size, orientation, and temperature, these structures could show up as unusual mid-infrared sources in sky surveys, much like how astronomers hunt for Dyson swarms, but with slightly different spatial and timing signatures. the timing of potential transits is also crucial. A ring at Earth's distance from the Sun, for example, would take about 1 Earth year to complete a full orbit, meaning its deepest shadow would pass in front of its star once per year, as seen from Earth. For tighter orbits, the pattern could repeat more often. Multiple rings at different distances would generate overlapping sets of dimming and brightening, creating a light curve fingerprint that, while difficult for nature to arrange by chance, would readily result from a carefully engineered project. The idea of ring worlds and stellar rings matters even more when put together with the other kinds of megastructure signatures astronomers look for. If an unusual dimming event occurs, telescopes can concentrate on that star to see if corresponding infrared excess waste heat or unnatural colour shifts appear. If all these measurements point the same way, the case for a structure as opposed to a dust ring or random cloud grows stronger. Likewise, repeated or evolving patterns across decades can hint at maintenance, expansion, or changing use, none of which matches the slow, random behaviour of natural rings. Looking at the physical requirements, constructing a ring at interplanetary distance is a staggering challenge. Even a thin band circling a star would require enough mass to build thousands of Earth's worth of material. No known planetary system, even ours, with its rich asteroid belt, could assemble something of that size without major advances in mining, robotics, and materials science. Some engineers have proposed using materials like carbon nanotubes or futuristic alloys, which would be needed to survive the incredible forces caused by fast orbits and the pull of gravity. Maintenance would also be an ongoing process. Micrometeoroid impacts, radiation, and gravitational tides would gradually wear away at any structure, even one under constant repair or replacement. Despite these enormous challenges, researchers use the same logic as with Dyson spheres. Even if construction is daunting, finding such a structure would be unmistakable evidence of intelligence operating at a scale much larger than anything on Earth. As with Dyson spheres, ring worlds would be bright targets for searches in both visible and infrared wavelengths. Some astronomical missions now build theoretical models for a variety of megastructures, including partial rings, completed ring worlds, and clusters of energy collectors, into their analysis software, making it possible to catch anomalies that might otherwise slip through the cracks. Another interesting aspect is that rings might not be used solely for habitation or energy. The nature of a ring means it could also act as a defense shield, act as a communication relay, or support agriculture and industry on a level beyond any planetary surface. Civilizations could reconfigure or expand the ring depending on changing priorities, or even break off sections to send to new orbits if needed. Some scientists speculate that rings could be the training wheels on the way to bigger and more complex swarms or shells covering all angles of a star, with the early ring sections eventually incorporated into the larger project. There have been attempts to look for unnatural rings in data from exoplanet hunts. Some light curves do show hints of big, flat-topped brightness dips, which could be explained by rings bigger than any found around planets in our solar system. However, in every case so far, after detailed analysis, dust clouds, natural debris disks, or rare alignments of known materials have accounted for the findings. Still, astronomers are always developing better statistical models to separate the rare, regular, and abrupt events from the sea of ordinary, naturally generated signals. In the last decade, with more telescopes dedicated to monitoring thousands of stars with high precision, our ability to spot even faint, fleeting transits has increased hugely. Artificial ring searches can now be automated, with computer algorithms set to sift through millions of stars' light curves, hunting for the right patterns. Future missions propose to scan entire swaths of the sky using multiple colors and new types of detectors, improving the odds of picking up the unique signal produced by an engineered ring. Ring worlds, stellar rings, and their hybrids are not only a favorite of science fiction fans, they are also practical signposts in the search for advanced life. Their shadows have clear, sharply defined entry and exit points. Their material compositions would create reflectivity and heat patterns distinct from natural dust or icy fragments. Their orbits could produce precise, clockwork, regular light dips, a key clue for any astronomer scanning the heavens for anomalies. And if detected, they would immediately raise big questions about the kind of society that could create and maintain such astonishing projects. By combining high-precision monitoring, improvement in computer modeling, and collaboration between professional astronomers and citizen scientists, the hunt for ring worlds and stellar rings is moving forward step by step. As more complex ideas are tested and more data is collected, the line between natural and artificial gets clearer. Every unexplained shadow, every perfectly timed dip, no matter how brief, brings the possibility of encountering signs of technology much further from our planet than we ever thought possible. So, as the search for alien megastructures continues, ring worlds and stellar rings remain central in both science fiction conversation and real science. They teach us that cosmic-scale projects come in many shapes, and that a careful eye might just pick out the signature of something truly unique happening far from our solar system. Each improvement in techniques, each new mission, and every better detector increases the odds that if such a structure is out there, we may one day spot its unmistakable pattern crossing a distant star, inviting us to ask new questions about what is possible in our universe. With all these ideas about ring worlds and other monumental projects orbiting stars, astronomers naturally shift attention to the question of how best to detect evidence of intelligent activity beyond Earth. This is where the modern search for extraterrestrial intelligence, known as SETI, really enters the picture. For decades, SETI was viewed mostly through the lens of radio waves. Scientists pointed gigantic antennas into space, hoping to catch a deliberate signal sent by another civilization. But over time, a new approach gained traction. Instead of just waiting for a message, researchers should look for signs of technology itself, what they now call technosignatures. The concept of SETI has been around since the early 1960s, almost as long as the very first practical ideas about megastructures. Initially, the focus was pretty narrow. The logic was simple. Technology on another planet might send out a strong and unmistakable radio pulse, something narrow in frequency and powerful enough to rise above background cosmic noise, and that would serve as evidence of its existence. Early experiments like Project Ozma in the year 1960, led by Frank Drake, used smaller radio telescopes to scan the skies nearby. As bigger and more sensitive radio dishes came online, the field expanded, moving from searching a handful of stars to surveying hundreds or thousands. Yet, after years of listening, no clear, repeatable signals ever came through, and leaders in SETI began reflecting on whether waiting for a handshake was the most productive approach. By the 1990s, technology and theory had both improved. Astronomers recognized that a civilization does not necessarily have to be sending messages for us to detect it. Technosignatures, a term that started gaining ground around this time, refers to any detectable evidence of advanced technology, whether intentional or a byproduct of activity. A radio beacon is just one subset. Others could include strange electrical signals, pulsed lasers, artificial light, signatures of industrial pollutants in exoplanet atmospheres, or, most notably, megastructures like Dyson spheres and ring worlds. This broader thinking aligned with how planetary scientists look for biosignatures, chemical clues like oxygen or methane that indicate life. With technosignatures, the game is expanded to all byproducts of civilization, not just deliberate attempts at communication, as more researchers learned algorithms for analyzing light curves, spectra, and energy output. The process of hunting for technosignatures became more systematic. In the case of megastructures, the search focused first on the kinds of signals and patterns that giant engineering efforts would cast into space. For instance, a Dyson sphere partially cloaking a star would cause unique dimming and a spike in mid-infrared radiation, both measurable with modern telescopes. A colossal solar array, satellites, or even advanced networks of power beams crisscrossing a planetary system could create ripples or abrupt cutoffs in electromagnetic signatures. When building the huge data archives produced by space observatories, researchers train machine learning tools to look for these telltale patterns. Dimming events that last longer, have sharper edges, or show irregular repetition, as well as heat emissions inconsistent with natural dust disks. However, not all technosignature searches are about light or heat. Some teams investigate the possibility of artificial structures producing signals in X-ray or ultraviolet wavelengths, or even gravitational ripples if the mass is enormous enough and in motion. Others pay attention to atmospheric changes, expecting that a hyper-industrial civilization could alter the chemical makeup of its planet's atmosphere, leaving signs like high concentrations of chlorofluorocarbons, smog-forming molecules, or unique artificial isotopes. With enough spectral resolution, future telescopes might compare the air around an exoplanet to Earth's, looking for the chemical fingerprints of industry. Radio SETI, meanwhile, has hardly faded away. If anything, it runs in parallel to techno-signature surveys, with both disciplines benefiting from the advances in signal processing and pattern recognition. New projects are dedicating high computing power to scan thousands of stars for narrow-band pulses, frequency sweeps, and broadband bursts. While nothing conclusive has shown up, the volume of data keeps growing, and each false lead refines the strategies for targeting interesting parts of the sky. One recent boost came from the discovery of exoplanets by ground-based and space-based telescopes starting in the 1990s and accelerating since the launch of the Kepler mission in the year 2009. For the first time, researchers had actual targets potentially orbiting in the habitable zone, planets roughly Earth-sized, at the right distance from their stars for liquid water. The catalogue of Earth-like and super-Earth worlds is now in the thousands, providing a practical target list for directed SETI projects. Rather than searching randomly, researchers can now prioritize stars with planet candidates, especially those showing light curve oddities or unusual spectral characteristics. This shift has made the search much more efficient, especially when coupled with data from observatories that work outside the visible spectrum. Another important improvement is international coordination. Since the 1980s, telescopes on different continents have collaborated to verify strange signals. If a blip pops up at Arecibo in Puerto Rico, for example, researchers scramble to check with facilities in Australia, Europe, or China. This helps rule out local interference, instrumental glitches, or known cosmic events like pulsars or flaring stars. The Megastructure hunt too becomes part of this network. If a candidate star dims sharply or emits odd energy, teams can quickly arrange multi-wavelength follow-ups, often keeping a potential techno-signature under watch for years at a stretch. Data sharing has reached an all-time high. Open-source databases now catalogue billions of light curves, energy readings, and candidate signals, inviting both professional astronomers and amateur skywatchers to dig in. Online citizen science platforms help sort anomalies, people flag rare patterns, and experts review the most promising leads. This distributed approach multiplies the eyes on the sky and helps catch rare phenomena that automated programs might miss, especially faint or fleeting techno-signatures that happen only occasionally. There's also been a big push to update the menu of what counts as a techno-signature. Dyson spheres, ring worlds, and massive satellite clusters grab headlines, but smaller scale or subtler signs are now factored in. Theoretical studies map out possibilities like laser flashes used for space communication, small fleets of artificial satellites that slightly modify a star's spectrum, or swarms of translucent structures designed to harvest specific wavelengths. Unnatural patterns of signals, whether bright, periodic, or strangely coloured, are all fair game as long as they repeat or present evidence for engineering beyond what normal physics would produce. Industrial pollution has entered the discussion in the past decade as spectroscopy tools advance. On Earth, certain chemicals like chlorofluorocarbons do not occur naturally and are only manufactured by industry. Astronomers working on the James Webb Space Telescope and similar projects are targeting exoplanet atmospheres with the idea that a dirty planet might actually be more recognizable as inhabited than a purely biologically driven one. These searches have yet to yield a true hit, but every new round of spectra helps refine the models and improve the odds of spotting subtle markers amid the noise. There's an important balance in all this work. While excitement over possible discoveries runs high, healthy skepticism is built into the process. Many natural systems can mimic artificial signatures, at least superficially. Dust disks around stars, collisions of large bodies, flares, and rare classes of variable stars all create signals that can look strange or regular. Each candidate event gets scrutinized in multiple ways: visible light, infrared, ultraviolet, and radio, making sure that only the best supported anomalies remain as possible techno-signature candidates. The bar for a real detection is high, but the reward would be enormous if new, strong evidence points to technology rather than natural processes. Computer science and machine learning now drive much of the search. Billions of light curves get processed by neural networks trained to pick up not just the obvious dips and flashes, but also complex patterns indicating groups of objects or engineered time signatures. As technology advances, false positives diminish, confidence goes up, and the odd candidate that cannot be explained naturally gets faster and more intensive follow-ups. These tools also help spot slow, long-term changes that might be signs of a civilization repurposing its star system, not just drawing power or building once, but adapting over centuries. High-level SETI and technosignature projects constantly re-evaluate what targets are worth attention. A star with unpredictable dimming, excess heat with no dust disk, and no known variable star behavior gets flagged right away. Light curves found to contain repetitive, precise patterns are double-checked for instrumental causes or echoes of satellite passes. Only when all standard explanations are exhausted does a signal remain in the running for potential artificial origin. There's strong international support for the hunt. Foundations, governments, and even private investors fund new telescope arrays and signal processing centers, understanding that the search for technosignatures is not just an exotic curiosity, but a long-term scientific and human mission. The growth of funding and resources means more time on sky, bigger collaborations, and more detailed studies, all working together to gradually whittle away the field of possible candidates. The biggest shift in outlook is how scientists no longer see the quest only as listening for a greeting from space. Now the focus is equally on the footprints technology leaves behind, especially at scales far beyond what humans can currently accomplish. Whether that footprint is in light, heat, radio, or even particle signals from strange forms of matter, scientists watch for any mismatch with known laws of physics as applied to stars, planets, and cosmic dust. Efforts are also underway to coordinate sky monitoring efforts so that unexpected events get rapid responses. If a star complexly dims or erupts in odd light, other observatories can schedule urgent observations across the electromagnetic spectrum within hours or days. This coordinated vigilance is leading to new ways to catalogue, classify, and prioritize events. The workflow, from initial detection to confirmation or dismissal, becomes ever more refined and swift. As these systems improve, the expectations adjust too. Astronomers are prepared for surprises. A true technosignature might not look exactly like the classic Dyson sphere pattern or the textbook radio beacon. It could show up as a sequence of heat pulses, a strange order in stellar flickering, or an altogether new kind of electromagnetic fingerprint. Researchers must walk a line between diligently following evidence and remaining open to the idea that alien technology might stretch or even break the categories science has built so far. Public interest in the search continues to grow as well. Podcasts, documentaries, and open data challenges invite anyone with a laptop and some curiosity to join the hunt. High-profile discoveries, even those that turn out to be false alarms, attract more eyes to astronomy and more volunteers to citizen science projects. This democratization keeps the field fresh, brings in unexpected expertise, and spreads workload across a global network of eager minds. In terms of results, it is still early days. No confirmed technosignature has yet been accepted by the worldwide scientific community as proof of extraterrestrial life or intelligence. Every potential sign gets checked, double-checked, and almost always ends up with a natural explanation. But with each improvement in sensors, data curation, and techniques, the picture being built grows sharper. And with each new cycle, the process becomes better at ruling out noise and better at highlighting real, unexplained oddities. Underlying it all is a continuous flow of new data. Science thrives on endless measurement and comparison, which is exactly what sky surveys and SETI megaprojects deliver. As more light curves, spectra, and infrared maps pile up, so does humanity's awareness of what is normal versus what stands out. When that day arrives and a technosignature gets through all filters, resistant to every natural explanation, showing unmistakable pattern or artificiality, astronomers will be ready to act quickly. Until that happens, the discipline focuses on improving both tools and interpretation, ensuring that when a real signal does come, it is recognized for what it truly is. With the combination of broader search strategies, ever-evolving technology, and a growing global community, SETI and technosignature research work hand in hand with the hunt for megastructures like Dyson spheres and ring worlds. The journey is gradual but relentless, responding to both discoveries and disappointments by refining the science step by step. Every method, every new piece of equipment, every citizen scientist's flagged anomaly all add up, giving humanity the best possible shot at noticing when the universe finally lets us know that we are not alone. As SETI researchers refine their approaches and technology continues to multiply our ability to scan the skies, astronomers keep stumbling on moments when the universe seems to flash something unexpected right at us. In the landscape of cosmic discoveries, there's a recurring pattern. A star flickers or goes temporarily dark. A faint signal buzzes briefly and then vanishes. Or something happens that completely sidesteps established categories in astronomy. These incidents, involving strange lights that blink, signals that burst in wild patterns, or stars that fade and brighten without warning, are collectively known as unexplained cosmic phenomena, and they often sit at the crossroads of science's understanding and its biggest open questions. One of the most famous recent examples involves so-called fast radio bursts, or FRBS. The first FRB was recorded in the year 2007, nearly by accident, in data from the Parkes Radio Telescope in Australia. It was a pulse of radio energy lasting just a few milliseconds, but in that tiny fraction of a second, it emitted as much energy as the sun does in a whole day. Since then, astronomers have catalogued hundreds of these bursts using radio antennas around the world. Most FRBs seem to be one-off events, appearing without any warning or follow-up, but a small subset repeat unpredictably, sometimes with gaps of days or years in between, which only adds to the mystery. Theories for FRBS abound. Some posit that colliding neutron stars, black holes, or the collapse of exotic objects might be generating them. Others have linked them to highly magnetized neutron stars called magnetars that can release tremendous energy as they restructure their own magnetic fields. But the fact remains that a few bursts have patterns difficult to match with any known cosmic event, especially the repeaters. In the rare instances where a signal repeats at odd intervals rather than at regular cycles, some researchers have cautiously suggested artificial origins, or at the very least, that we might be dealing with an astrophysical process with no direct counterpart in our own solar system. Another kind of unexplained cosmic blinking comes from the field of optical astronomy. Every month, automated sky surveys like Zwicky Transient Facility and Pan-STARRS collect terabytes of data tracking the brightness of millions of stars. In this sea of information, automated routines sometimes flag objects exhibiting sudden, deep, or strangely shaped dips in brightness. Tabby's star, which dropped in brightness by over 20% in irregular, unpredictable ways, is still the benchmark for these odd tumblers, but it is far from alone. Astronomers have encountered several lesser-known stars with sharp dips, sometimes symmetric, sometimes jagged or multi-stepped, most of which challenge immediate explanation. Sometimes follow-up reveals complex planetary systems, sometimes dust, but a percentage remain outliers that fuel more searching. Some stars are variable by nature, but it's the ones that act outside known categories that get attention. Regular variable stars change their brightness on well-understood cycles, often based on their internal structure or the way they interact with a companion. When astronomers spot a star that pulses erratically, loses brightness for long stretches, or pulses with multiple timescales not linked to stellar evolution, questions start to pile up. Is there a cloud of orbiting debris blocking the light at odd intervals, a planet with massive rings, or something even stranger? The fact that these objects do not fit the predictable models makes them fertile hunting grounds for candidate artificial megastructures. Another area ripe with cosmic blinking comes from survey missions that monitor thousands of galaxies at once. Occasionally, a galaxy flares up in infrared or X-ray wavelengths for no obvious natural reason. In other incidents, entire star clusters appear to dim or brighten as if affected by eclipses, but no single planet or dust cloud could plausibly cause such a synchronized effect. Rarely, a single luminous object will vanish entirely from sky catalogues, prompting astronomers to double and triple check archival images to search for instrument errors or misclassifications. Often, dust drift or star death is the answer, but not always. Beyond single bizarre cases, astronomers have noticed odd regularities that defy easy explanation. For instance, in a handful of instances, objects have flickered in ways that resemble mathematical constants or repetitive digital sequences, like the famous "wow" signal captured in 1977 that lasted roughly 72 seconds and has never repeated. While most of these events turn out to be terrestrial interference or random statistical blips, they force astronomers to keep refining detection methods and building better filters to weed natural from artificial. In recent years, coordinated observation campaigns have helped chase down the most fleeting of these blinks. Multiple observatories can now watch the same object almost simultaneously in different wavelengths. If an impossible pulse or dimming pops up in optical surveys, researchers can quickly ping radio, infrared, or X-ray telescopes to see whether the anomaly extends beyond visible light. In some cases, strange phenomena are caught in more than one part of the spectrum, which means models have to catch up fast. Each cross-checked observation helps researchers narrow the list of possible culprits and eliminate chance or instrument error. Technological glitches are also a constant background issue, and astronomers spend enormous time ruling out false positives. A cosmic ray can hit a detector and briefly mimic a blinking star. A passing satellite might scatter light in such a way as to momentarily simulate a natural event. Even the software that processes all this sky data develops bugs and patterns that occasionally produce phantom events. This is why, whenever a truly strange event occurs, it takes months or years of double-checking, often calling on archives going back decades to see if anything similar happened before. Blips and bursts also come in clusters. Scientists sometimes observe not just one star, but a whole region of the sky blinking, dimming, or lighting up over minutes or hours. In some cases, this is linked to cosmic rays, supernova shockwaves, or tidal disruptions by black holes. Other times, the scale and repetition just do not match anything explained by current physics. These rare, massive events lead to hundreds of follow-up projects across observatories worldwide. Even after careful study, a few always linger as unsolved mysteries on the edge of astrophysics. Some researchers actively search for artificial patterns in these episodes by looking for evidence of engineered intent. Things like phase shifts, abrupt regularity, or light levels consistent with megastructures changing shape or position. A cluster of objects blinking in sync without a natural explanation is flagged as a techno-signature candidate, although so far every case has eventually run into natural answers or issues with measurement. This repeated process keeps the field honest and cautious, but also makes sure nothing slips through if real artificial behavior is ever present. Another angle comes from time-domain astrophysics, where astronomers monitor the same stars for weeks, months, or even years. Instruments like NASA's TESS or the European Space Agency's Gaia collect long-term data on a select group of stars. When an object starts dimming or brightening on timeframes that cannot be explained by rotation, orbit, or aging, these light curves attract careful scrutiny. Occasions where dimming happens only once over many years, or recurs with no obvious planetary or stellar cycle, often trigger long-term observation campaigns. Apart from light signals, there are also mysteries in radio astronomy outside just FRBS. Some radio bursts have appeared to repeat at semi-regular intervals with odd gaps or intensity fluctuations. Others cut off abruptly or change character in the middle of a sequence, unlike known natural false positives. While most are connected to neutron stars, magnetars, or even blasts from solar flares in our own system, a handful are labelled unknown origin and left open in catalogues for further study as methods improve. Sometimes strange cosmic disappearances make headlines. In one case, an entire star seemed to vanish from repeated sky surveys over decades, leading to speculation about whether it collapsed directly into a black hole, was obscured by a huge dust cloud, or even cloaked in some kind of artificial structure. These vanishings generate follow-up, using every tool in the astronomical toolbox, hunting for faint X-ray or gravitational clues. Even when mundane explanations win out, the fact that we are monitoring billions of objects so closely gives every astronomer a list of cases they keep an eye on, in case a pattern emerges with new data. Across all the unexplained cosmic phenomena, the unifying principle is skepticism and patience. Teams assume a natural cause until it is repeatedly tested, modelled, and ruled out. The history of astronomy is filled with cases where new classes of objects were discovered after following up on odd light or energy bursts. Quasars, pulsars, and gamma-ray bursts all started as lights that shouldn't blink before their true nature was worked out. But astronomers are increasingly aware that as data grows in quality and quantity, the space for new findings, including those linked to possible technology, remains open. Automated algorithms now flag odd blinks, burps, and dips from the fire hose of data pouring out of sky surveys, but the final call almost always comes back to careful human review and months of hypothesis testing. Researchers dig through historical records to look for overlooked patterns, test whether a weird light flash aligns with a satellite crossing, or even check whether interference from city electronics might have shaped the data. In the end, the catalogue of unexplained cosmic phenomena acts as both an inspiration and a warning. Every star that flickers in an inexplicable way, every radio pulse that zips through the night sky and vanishes, every temporary darkening or flare brings us closer to mapping the full landscape of what our universe can do. The narrowest cases, where clues do not quite fit any present theory, are where astronomers sharpen their tools, tighten their skepticism, and keep their eyes open for evidence that somewhere a technology might be at work. The balance, as always, is to gather as much good data as possible, refine theories using every available tool, and stay honest about what remains genuinely unknown. It is through these unexplained flashes, blinks, and vanishings that astrophysics progresses, turning puzzling events into new classes of objects, or, just possibly, into the first signs of intelligent life beyond our world. The search is ongoing, propelled by curiosity, careful data cross-checking, and the humble admission that, even with all our instruments and expertise, the night sky keeps throwing surprises our way. Because the night sky constantly reveals unexpected flickers, bursts, and disappearances, astronomers need every possible tool to tell apart a natural event from something that might be engineered. Among all the strategies, searching for waste heat stands out as one of the most clever and practical. The logic behind it is rooted in basic physics. Any big machine, whether it's running a household device or powering a cosmic megastructure, soaks up energy and then has to get rid of what it can't use. With that principle in mind, if a civilization is harvesting massive amounts of energy from a star, there is bound to be excess heat radiating outward, especially in the form of infrared light that our telescopes can catch. Detecting waste heat isn't a new idea, but it has grown stronger in the last few decades as infrared astronomy matured. In the year 1983, the launching of the Infrared Astronomical Satellite, also called IRAS, was a milestone. It was the first telescope to scan the entire sky in infrared, mapping cosmic heat sources that are invisible to our eyes. Even then, scientists dreamed of using this sort of data to hunt not just for galaxies and star-forming clouds, but for oddball signatures that could mean artificial energy use on a huge scale. Later missions, such as the Wide Field Infrared Survey Explorer, WISE, launched in the year 2009, gave astronomers ever sharper and more detailed maps of the sky's infrared emissions. If an advanced civilization built something like a Dyson sphere or sprawling swarms of satellites, they would block much of their star's visible and ultraviolet light. However, all the absorbed starlight has to go somewhere. Since nothing is perfectly efficient, the energy gets re-radiated as lower temperature heat, peaking in the mid-infrared part of the spectrum. A search for this extra signature is like looking for a glow around stars that shouldn't be there, which serves as a possible indicator that something is using up starlight much more aggressively than dust or gas naturally would. Astronomers have a few ways of going about this. One approach is to look for infrared excess in stars that shouldn't have it. Most stars have predictable amounts of heat, depending on their age, type, and whether they have dusty disks. If a star glows brighter than that calculation, particularly in mid to far infrared wavelengths, it's worth another look. Another method is to focus on stars with strange brightness dips, as seen in ongoing exoplanet studies. If a star dims weirdly and also radiates more heat than expected, it gets flagged immediately for follow-up. Of course, dust and debris throughout a galaxy emit lots of infrared as well. Newborn stars, old giants shedding their outer layers, and regions rich in broken-up asteroids or comets produce heat as a matter of course. But trained astronomers compare these natural sources with models of what an artificial megastructure would do. For instance, dust often produces broad, smooth heat signatures, and the source of that dust, like a forming planetary system or a recent collision, usually shows up in other wavelengths or with distinctive patterns. An engineered construct, by contrast, might have sharper or more stable unstable infrared signals or appear in systems with no reason for such a glow. When analyzing WISE and IRAS data, teams use software to match millions of stars to known normal values and spot outliers. They filter by star age, temperature, location, and whether the candidate sits in a crowded, young, or disruptive part of the galaxy. If a star stands out with an excess heat signature that doesn't match any natural scenario, researchers dig deeper. They check against galactic dust maps, rule out background galaxies hiding behind the star, and cross-reference with catalogues to see if the same star has already been noted as odd for some other reason. Over the past few decades, a handful of interesting candidates have turned up. One famous IRAS find from the late 1980s was a star called HD 1086, which showed excess heat typical of a debris disk but did not match expectations for dust or young planets. In the end, further study showed most candidates like this can be explained by rare but natural events, such as massive dust production after a collision between planet-sized bodies. Yet, for a small but persistent number, detailed modelling leaves the cause uncertain. They are put aside for re-examination with future, more sensitive missions. Astronomers are also expanding these searches to whole galaxies. The idea is that a truly advanced Type 3 civilization, according to the Kardashev scale, could harness energy on scales spanning billions of stars. If so, a galaxy might glow slightly brighter or hotter in infrared than in visible or X-ray light. So far, every galaxy studied in detail seems to fall within what is expected from known star formation, dust clouds, and black hole accretion. But as survey data improves and covers more distant and older galaxies, there's always the chance something unique or unexplainable will pop up. Another layer of sophistication comes from looking at the spatial structure of the heat emission. A Dyson swarm might not cover a whole star evenly. Bits could be missing, creating non-uniform but repeated blobs of infrared. Modern imaging techniques can sometimes resolve the location of heat sources and compare these shapes against models of partial megastructures. For now, even the best data just barely approaches the resolution needed, but missions in planning for the next 2 decades promise sharper imaging and multispectral views. On the technical side, the temperatures astronomers look for are usually a few hundred Kelvin, well below a star's natural surface, but well above the frigid background of deep space. This temperature range is where starlight, once blocked or captured by a solid object, would be re-radiated as heat. Materials like metal, glass, or polymers, if used by an alien builder, have unique fingerprints in this region. From space, a really energetic megastructure would resemble a cool shell around a hot core, with the shell glowing mostly in the mid-infrared. It's important to understand that most searches for waste heat are extremely statistical. Because there are billions of stars and dust clouds, astronomers leverage machine learning and pattern recognition. The software sifts through catalogues, tags, anomalies, and then the human researchers follow up. In many cases, these anomalies turn out to be errors, rare natural clouds, or even faintly glowing background galaxies seen along the same line of sight. Still, every confirmed outlier is a chance to learn more about the full variety of objects in the universe and to refine the search further. One interesting trend is the growing overlap between infrared excess features and known sites of high comet or asteroid activity. For instance, some systems rich in comet belts, like our solar system's Kuiper belt, are expected to radiate extra heat. However, those belts have telltale patterns that astronomers can see in other wavelengths, like scattered reflected sunlight or temporary outbursts. Any anomaly that shows extra heat with no expected debris or other activity stands out. To dig deeper, astronomers frequently check these oddballs with as many telescopes as available. A star with unexplained heat gets tackled with visible light telescopes, radio arrays to look for transmissions, and sometimes even X-ray or gamma-ray observations. The goal is to cross-check for any other signs of activity that might hint at an artificial cause, a strange dimming, flickering, or radio pulse in sync with the heat change. The absence of supporting signals doesn't prove anything either way, but the accumulation of negative or ambiguous results forces a focus on getting better data with every new generation of surveys. With each passing year, as technology improves, new missions boost the hope of finding genuine standouts. Upcoming telescopes, both ground-based and space-based, are designed to sense even fainter and cooler objects in the sky. They will track even more stars, look further into the galactic core, and push the limits on what size of heat source can be distinguished from background noise. If megastructures artificial in origin exist at any reasonable frequency, there's an expectation that coming decades will reveal at least a handful of clear events. Another recent area of development is the interpretation of spectral lines, the finer details of how an object's heat is distributed across exact wavelengths. If a megastructure uses specific materials, those might slightly tweak the infrared emission in ways different from ordinary silicate or carbonaceous dust. Comparing highly detailed spectra from multiple stars, astronomers hope to catch these unique fingerprints, further narrowing the candidate list. Several teams are building libraries of likely alien engineering spectra, testing against everything from hypothetical plastics to metals that could handle the extreme conditions near a star. A practical challenge in these searches is that astronomers must separate the millions of ordinary objects with some extra heat from the few genuine oddballs. Natural processes account for the vast majority. Newly formed stars, stellar mergers or collisions, stars dying and shedding mass, even larger than average asteroid collisions, all create heat. But consistent patterns, repeated structure or strong heat with no matching dust or gas are still seen as clues worth follow-up. Astronomers accept that, with so much cosmic activity, any positive identification will have to be supported by more than just one signature. It'll take a mix of timing, pattern, and lack of natural explanations. Waste heat searches are also valuable because they are blind to intent. They do not require catching a transmission or interpreting a signal as a deliberate hello. Any civilization using lots of energy has to get rid of heat, whether or not it wants to be seen. That makes infrared a universal technosignature, one that should show up no matter how technology is designed or what its purpose is. The universality of physics means that even alien methods of energy capture and use must radiate at least some heat. This fact keeps astronomers coming back to heat as a baseline sign that something might be happening beyond the reach of natural evolution. In all this effort, negative results are as meaningful as the rare potential hits. If surveys keep coming up empty in a certain part of the sky or for stars of a certain type, it sets limits on how common these sorts of civilizations or their megastructures might be. These constraints actually refocus research on where the odds of finding something unexpected may be the highest, perhaps in parts of the galaxy less prone to starbirths, or among older solar systems where dust clouds have mostly dissipated. Tracking where anomalies definitely are not is as helpful as knowing where they crop up because it narrows the statistical gap. Despite decades of careful searching, there hasn't yet been a smoking gun, one unquestionably artificial heat source outshining natural explanations. All credible candidates so far require more study, and every mystery investigated adds new details to sky catalogues. With each improvement in sensors and more data coming in, the pool of unexplained objects grows smaller, but every remaining one is now checked at a higher and higher level of scrutiny. Searching for waste heat also motivates creative thinking among astronomers and engineers. As more is learned about natural dust, comets, stars, and their irregular activities, researchers keep updating their models for what a real Dyson swarm or ring world would do, filling in every what-if with numbers as computers improve. They take known candidates and run simulations, tweaking variables like orbit, material, age, and purpose to see how heat patterns would look from Earth's perspective. This collaborative, iterative process helps refine not just the search for extraterrestrial megastructures, but also our core understanding of how the cosmos works. Finally, as more discoveries come in, interest and excitement are building in both the astronomical community and the public. Every odd heat fingerprint, especially one with no dust, gas, or other natural counterpart, brings renewed attention, debate, and the desire to build better and more sensitive telescopes. The race is on, and every year brings us closer either to a breakthrough or to a definitive understanding of what infrared sky surveys can tell us about alien engineering. Until then, scientists continue to watch, measure, and debate, knowing that waste heat is one of the purest and most reliable clues the universe has to offer in answering the ultimate question of whether we are alone. As astronomers push further in their search for unusual waste heat and ever more advanced sky surveys keep producing bigger piles of data, there's a central tension that guides the whole process. How do you filter out the wild possibilities from the wild facts? Most of the time, when an unexplained signal, burst, or odd pattern in data turns up, the very first step is to go through a mental checklist of natural explanations. This is a foundation of scientific investigation. The idea is simple. Nature is full of surprises and oddities, and only a small handful might truly require new physics or something artificial. In the world of cosmic mysteries, the discipline of eliminating natural causes helps astronomers avoid being fooled by rare but ordinary astrophysical events. Every new candidate, maybe it's a strange dip in a star's brightness, a weird color in infrared, or a fast radio burst that looks out of place, gets tossed into this process. Right away, scientists ask, is this something with a well-known explanation? Could it be equipment error, an obscure variable star class, a weird dust cloud passing in front, or even a background galaxy whose light is blending in with the target? For each, yes, the search stops right there, and the catalogue of the universe's weirdest features gets one new natural phenomenon. This is how science builds confidence before anyone even whispers about alien megastructures. Looking closer at how these investigations play out, you see just how many strange effects the universe throws at us. Let's say a telescope picks up a star that repeatedly dims in irregular patterns, much like the historic case with Tabby's star. The team immediately digs into all the records: space telescope light curves, color spectra, high-resolution images. Often it turns out to be a dust cloud orbiting the star, a disk of young planets, or even a set of overlapping exoplanet transits whose timing happens to look odd. Older stars might be losing their atmospheres, which creates veils of gas and dust that block and scatter light in lumpy, unpredictable ways. Other times, gravitational microlensing, when another star or dark object passes exactly between us and the target, creates the illusion of dimming, bending light in ways that are rare but not impossible. Equipment glitches are another pervasive challenge. Space telescopes and ground arrays are sensitive tools, but they can pick up stray signals from cosmic rays, nearby satellites, or even electrical blips on Earth. One famous incident at the Parkes Observatory in Australia was linked back to a microwave oven in the staff break room. The signals looked a lot like fast radio bursts, but they turned out to be lunch. Every strange signal is now double-checked between multiple observatories, different wavelengths, and cross-referenced against the schedule of satellite passes, radar pulses, and atmospheric interference. Even persistence in a signal is not always a ticket to the unknown. Certain types of variable stars just don't behave the way textbooks say they should, only revealing their true behavior after years of close monitoring. Flares or pulses can come and go as a star's magnetic field snaps, or when two stars trade matter in a close binary system, resulting in complicated and sometimes highly repetitive light curves. The discovery of pulsars provides the perfect example. Their fast, regular pulses stumped astronomers in the 1960s before neutron stars were firmly understood. A major focus is on cosmic dust and gas, especially in younger systems where planets are actively forming. Disks of matter swirl around new stars, and clumps or gaps naturally block out starlight at odd times. In systems with big impacts, like an asteroid crashing into a planet, the event can throw off clouds of dust that create sharp, deep dips in brightness. Sometimes these dips repeat, but with slightly shifting timing or profile, tricking even the best software filters into thinking they are ultra-regular events. The more astronomers see these incidents, the sharper their models get, and dusty imposters are eliminated with more and more confidence. Another natural explanation that frequently comes up is the presence of background objects. When a telescope stares at a distant part of the galaxy, it's often peering through layers of stars, dust, galaxies, and random debris. Occasionally, an object along the line of sight perfectly overlaps with something much closer or farther away, creating funky light curves or heat signatures that at first glance look out of place. Checking against deep field surveys and catalogues, analysts can strip away hundreds of these photobombs before the search for artificial activity even starts. Sometimes coincidences do the trick. A planet with an extremely wide set of rings or a cloud of moonlets in an aggressive tilted orbit can cross a star's face and generate a pattern never seen before. Jupiter and Saturn offer inspiration. Their rings, shadows, and dozens of moons cast temporary dimmings and brightenings from Earth's point of view. Simulating orbits in detail, using everything we know about gravity and planetary formation, gives researchers the confidence to say when a light curve is better explained by natural architecture than something constructed by intelligent life. There's also the rare but real phenomenon of stellar eruptions and unpredictable outbursts. Massive stars sometimes blow off layers of their atmosphere without warning, or even swallow up smaller companion stars. These processes create sudden, dramatic brightening or fading that doesn't match normal variable star cycles. Over the years, supernovae, exploding stars, and kilinovae, collisions between neutron stars, have shown up as weird flashes, only to be sorted out after follow-up spectra reveal telltale chemical signatures and expansion speeds. On top of that, astronomers have discovered new types of cosmic energy sources simply by investigating unexplained phenomena. Gamma-ray bursts, short, powerful flashes recorded by space telescopes starting in the 1960s, weren't understood until decades later, when multi-wavelength follow-ups revealed their connection to the deaths of massive stars or the mergers of compact objects. Every mystery light in the archives offers the possibility of adding a new chapter to stellar physics, but the bar for claiming something totally new gets higher with every discovery. With the increasing power of machine learning and automated sky surveys, it's possible to process enormous numbers of stars and galaxies for signals outside the norm, then flag these for human analysts to sort. These tools work by learning what millions of natural light curves or spectra look like, then popping up the truly oddballs. It is still up to scientists to check each candidate against every known natural process, from binary stars and crowded stellar nurseries to background supernovae and gravitational lensing. None of this means that the search for megastructures or signs of technology is discouraged. In fact, the constant push to eliminate natural explanations makes the process of finding something truly extraordinary much more robust. For a signal or anomaly to be accepted as an artificial megastructure candidate, it must survive round after round of elimination. Not just new star types, but the weirdest astrophysical processes, overlapping lines of sight, challenging orbital mechanics, or imaging artifacts. Take the example of waste heat from the last discussion. Most stars with excess infrared have it thanks to dust or asteroids, which conveniently show up in visible or radio studies of the same region. To move a candidate forward, astronomers must demonstrate that the extra infrared light cannot be accounted for by any of the known sources. No dust, no asteroid belt, no colliding bodies. That's why so much effort goes into building up detailed multi-wavelength catalogues and into modelling every dusty cloud and reflective ring in the sky. The importance of cross-checking with independent data sources cannot be overstated. If a blinking star looks artificial in one telescope, astronomers turn to others working in different parts of the spectrum and often at different locations on Earth or in orbit. Only persistent, repeating, and cross-confirmed signatures escape the net of easy answers. The same goes for radio bursts, odd colour emissions, or unexplained vanishing of stars or galaxies. Before being promoted to the truly unknown, every anomaly is battered by the hardest tests scientists can invent. It is in the handful of cases that remain unexplained after all this work that curiosity heats up. These are the stars where dips recur over years, or the radio sources that pulse at non-random intervals for which no known natural system fits. Astronomers catalogue these, sometimes in public databases, as open questions for future missions and new theories. The list is never very long, but it's never empty either. New technology and broader sky coverage mean even stubborn anomalies are re-examined as next-generation tools come online. Researchers know history is full of cautionary tales. More than once, signals hailed as potentially artificial, sometimes even with headline excitement, have ended up as cleverly disguised natural phenomena, instrument noise, or even human interference. It's now standard to approach each new find, assuming nature has one more trick up its sleeve. Only after that assumption fails, often years later, does a new chapter begin. A related issue is that real alien megastructures might be subtle or radically different in appearance from what current theories predict. If a civilization uses totally new kinds of materials or finds a way to move energy without radiating much heat, the signal could slip entirely under the scientific radar. Astronomers keep this in mind, making sure the unknown file is always open to surprises. Some teams specialize in finding abstract patterns, such as signals repeating in prime number sequences or spatially coordinated blinking, which are harder to mimic by chance. Sometimes, researchers lean on interdisciplinary support, using planetary science, chemistry, or even artificial intelligence to build new models for what's possible. If something odd looks a little like a certain geological or chemical fingerprint, they rope in specialists to see if a natural substance can behave just so. If a binary star or a rare mineral can create the pattern in question, the anomaly gets reclassified and another lesson is added. This flexible, collaborative approach makes the frontier between natural and unnatural move steadily forward. Ultimately, the lesson from decades of sky searches is not that megastructures or alien technology don't exist, but that nature is sneakier and more creative than anyone expected. Every time a new form of star, galaxy, or cosmic explosion is discovered, the filter separating natural from artificial gets sharper. That is why the search for extraterrestrial signatures is so deliberate. Researchers know they risk missing real signals if they jump too quickly to conclusions, and also risk embarrassing mistakes if they don't check for every natural shape and shadow first. With more telescopes coming online, software getting smarter, and datasets expanding with every new mission, the process for explaining cosmic oddities will only get tighter. New standards for proof are set all the time, and the catalogue of known cosmic phenomena grows by the day. While the dream of finding something that can't be explained by dust, stars, or the random happenings of a vast universe is alive and well, science continues to move forward thanks to a discipline built not only on dreaming, but on knocking down each candidate with the best tools we have. So whenever an exciting new blink, heat source, or burst comes across the wire, rest assured that behind the scenes, astronomers are busy putting science to the test, chasing every natural explanation with persistence, determination, and just enough curiosity to ensure that if there really is something extraordinary out there, it will be recognized for what it is. With astronomers working harder than ever to rule out every possible natural explanation before considering anything artificial, the impact of a confirmed alien megastructure discovery would be hard to overstate. Imagine the moment when, after decades and even centuries of careful watching and checking, a star or a cluster of stars reveals patterns of dimming, heat, or energy output that absolutely cannot be chalked up to dust, gas, stellar evolution, instrument error, or anything in the vast catalogue of known cosmic phenomena. If such a case passed through all the filters and checks science can apply, the result would be astonishing, a true realization that humanity is not the only advanced technological player in the universe. The very first thing that would happen is rapid verification and documentation. Scientific teams would scramble to confirm the finding using totally independent observatories. Telescopes across every wavelength, visible, infrared, X-ray, and radio, would be repointed to the candidate. This global focus would not be about secrecy, but accuracy. Confirmation would involve rechecking raw data, running every calibration again, and challenging teams everywhere to try to disprove the result. Transparency, speed, and teamwork would be the order of the day. Astronomers would want to make sure that a single artifact from a cable, a random flicker in a detector, or an overlooked meteor trail would not risk the credibility of such a monumental claim. Governments, scientific bodies, and media would all start to circle. The discovery would jump instantly from specialized journals and sky surveys into press conferences and round-the-clock news reports. Leading astronomers and project heads would walk the public and policymakers through the evidence. Any uncertainties, caveats, or blank spaces in our understanding would have to be honestly presented, because the discovery would quickly become the most scrutinized scientific event in modern history. In all likelihood, teams would also reach out to other agencies and international partners, whether it is NASA, the European Space Agency, or the Chinese National Space Administration, to guarantee broad, coordinated access to data and cross-verification. One major shift would come in the lines of questioning. Instead of, do alien megastructures exist? The new questions would be, how old is it? How was it built? How much energy is being used? And perhaps most intriguing, is there still an operating civilization there now? The scientific community would launch an all-hands effort to harvest every possible bite of information from backup data, old sky surveys, and ongoing observations. Retrospective scans of the target area could reveal if the signature appeared suddenly or over time, if it has ever changed, or if there are slow shifts indicating repairs, reconfigurations, or even expansion. Every subtle variation in light, heat, or other emissions would be combed for clues about the builder's technological level, habits, and organizational capacity. Governments around the world would get pulled in, though not necessarily in a negative way. Agencies would see this as a fundamental moment for humanity, prompting official panels and councils of both scientists and advisors in social sciences, communications, and defense. National leaders might release public statements or call special sessions to address the scientific and cultural significance. It would be vital to keep the conversation factual, calm, and rooted in observable evidence, as wild speculation could easily confuse the early days after discovery. International organizations like the United Nations could quickly call briefings to coordinate peaceful information sharing and prevent misunderstanding. Public reaction would be intense, and there's every reason to expect that interest would cross all boundaries. Language, culture, age group, and even educational level. People would want to know what it means for science, theology, human purpose, and the future. Schools, community leaders, and religious organizations would all be drawn into the discussion, each looking to understand how this new knowledge fits their worldview. Some people might feel unsettled or overwhelmed, while others would feel hopeful or validated in their belief that life is common in the universe. Psychologists, educators, and science communicators would play important roles in translating the discovery in a way that is accessible and accurate. For researchers and engineers, the announcement would mark the beginning of an intense, multi-year and likely multi-decade research campaign. The technical questions would be relentless. Top priorities would include characterizing the size, shape, orbital pattern, and physical construction of the observed structure. Engineers would compare the detected megastructure against every current material, manufacturing method, and imaginable technology. Could it have been built with known elements? Or does the data suggest the use of exotic materials, energy fields, or unknown forces? If the megastructure was in any way incomplete or evolving, astronomers would want to know how quickly its pattern is changing. Does it suggest ongoing maintenance, rapid construction, or long-term decay? Astronomers would also scour the region for secondary signals. If the megastructure worked the way many models suggest, there could be associated waste heat, intense but regular pulses of energy, or even signs of traffic, smaller objects passing across the star, or modulations in output that might mean energy transmission to surface settlements, or even spacecraft. Radio telescopes would listen for any patterns, whether persistent hums in odd frequencies or short bursts that could hint at communication. If present, these measurements could provide a treasure trove of information about the engineering methods, power output, or even possible intentions behind the structure. Computer scientists and data analysts would run models around the clock. Simulations could test everything from the likely stability of a Dyson swarm built of trillions of collector satellites, to the physics of mega rings or shells, to the longevity and repeatability of energy management systems at that scale. Big questions to answer would include whether the structure looks perfectly orderly or slightly chaotic, what behaviors are possible for self-repairing tech, and how likely it is that the original builders are still alive and benefiting from the massive investment required. Some scientists would also check how visible the signal would be from other parts of the galaxy and estimate how many other civilizations could have noticed the same phenomenon and drawn similar conclusions. As information accumulates, attention would turn to how the discovery fits into the broader cosmic landscape. If an alien megastructure is possible around one star, how common are they elsewhere? Astronomers would look for similar signals in sky survey data. Has the same signature been overlooked in other star systems or even other galaxies? Every detectable feature, waste heat level, dimming curve, timing, and even spectral lines, would be run through archives to spot matching cases. Teams would propose new, targeted sky surveys, crowding telescope time to recheck past candidates like Tabby's star, and to scan especially promising classes of stars or stellar neighborhoods. Over time, the focus could move from basic detection to attempts at understanding intent and design. If the megastructure changes over years or decades, whether expanding, shifting, or suddenly going silent, it could suggest agency, ongoing use, or even a timeline for technological progress on a scale much bigger than any human institution. Combined with the structure's estimated age and energy throughput, these facts could help answer big questions about technological risk, longevity, and even hypothetical extinction events. If the detected structure radiated energy in deliberate patterns or regular pulses, Attention would surge over whether these are attempts at communication or simply engineering artifacts. Parallel to the excitement, there would be a cross-disciplinary debate about whether and how to try to send a signal back. Some might argue for listening longer, waiting to gather more evidence of activity or communication protocols before saying anything. Others would want to design a modest, information-neutral message to show that humanity is paying attention. An international process might develop with input from governments, scientific organizations, ethicists, and the public. There could be extended debates over the risks and benefits, the contents of such a message, and how to interpret any response or lack thereof. No matter what, a verified alien megastructure would force a massive recalibration of humanity's understanding of itself and its history. Theories about the frequency and distribution of advanced life would shift. The Great Silence, or Fermi's paradox, the question of why we haven't already found signs of aliens, would have a concrete counterexample. Models of evolution, planetary formation, and cosmic timescales would be updated to include at least one known example of successful, large-scale engineering by another species. This would shed new light on how intelligence and cooperation might develop, what obstacles can or cannot be overcome, and what the technological future might actually look like beyond science fiction. The new reality would impact SETI, astronomy, physics, and engineering for decades. Research funding would increase, likely at a huge scale, with new missions quickly designed to focus on further discovery and new methods of observation. Engineering and technology development would be inspired not just by curiosity, but by the hope of learning from data about the megastructure, tricks of construction, energy collection, or self-sustainability that could help human industry. Whole generations of students and young scientists would enter academia with the dream of learning more about the builders and their creations. Museums, curriculums, and media would adapt to explain the concepts and discoveries for every age group. Philosophically, the finding would redefine many people's views about humanity's place in the universe without needing to resort to far-fetched or mystical language. It would mark humanity's graduation to a wider community of intelligent life, maybe not as a participant, but at the very least as an observer aware of the scale of cosmic civilization. Social and political impacts could emerge as societies reckon with new contexts for their existence and future. Every field would have to integrate the implications. Historians would reinterpret records and culture, philosophers would revisit questions of meaning and destiny, and leaders would reconsider priorities in research, exploration, and international cooperation. Beyond immediate excitement, there would be a long-term need for ongoing observation and data curation. The original megastructure finding would have to be tracked for decades, possibly centuries, to note changes, repeat measurements, and collect any evidence of behavior or adaptive design. If future observatories spot new structures elsewhere or variations in the original, patterns could develop and help explain life cycles, energy demands, or decline and renewal among cosmic superprojects. Future missions, possibly using spacecraft driven by next-generation engines, could aim to fly closer to the source, perhaps attempting to send mini-probes or sophisticated relays that report back detailed observations. The broader cultural impact would echo across arts, education, and public imagination. New books, movies, games, and documentaries would try to put the discovery in context, focusing on everything from the engineering complexities to the social ripple effects. There could be a sustained burst of creativity as writers and thinkers use the event to pose new questions about exploration, cooperation, and possibility. The phrase, "we are not alone," would stop being a matter of speculation and become a historical fact, changing language, routine conversation, and education at every level. For everyday people, the discovery could affect how we look at the night sky. What was once seen as a distant, unreachable expanse becomes evidence of life and technology thriving elsewhere. It might inspire more people to study astronomy, engineering, communication, or the natural sciences. It could motivate renewed interest in planetary protection, space law, and the ethics of expanding human activity in the solar system. People might track news updates as scientists map new structures or decode new patterns, and families could follow the timeline of missions seeking follow-up observations. In all, a bona fide alien megastructure would act as a pivot point for our entire species. The discovery would set in motion a high-speed sequence of scientific, technological, social, and cultural changes, each linked to the chain of evidence collected in that very first world-shaking observation. Over years and decades, this one signature in the sky could influence everything from school science classes to global research budgets, and from diplomatic agreements to the shape of popular storytelling. This is not just hype or speculation, as challenging as it has been to get to the point where astronomers can even talk seriously about megastructure detection. The process is built on science's strictest habits. Every step, from initial detection to final confirmation, would be guided by the lessons learned from previous mistakes and successes. Careful cross-checking, full transparency, international cooperation, and a sense of proportion between open-mindedness and skepticism. Only with this solid base could the discovery hold up to the scrutiny and importance it would demand. For all the years humans have looked up and wondered whether they are alone, the presence of a definite alien megastructure would at last offer a data-driven answer. Even if contact or communication never follows, the knowledge that other civilizations have not only existed but have managed to engineer on a scale far larger than anything on Earth would change what it means to be human. The universe would instantly become a bigger, more crowded and more fascinating place. Astronomy, science, and society would have their next grand adventure mapped out, and the process of understanding, exploring, and living with that knowledge would truly begin.